TI now for about 14 years, writing activities, doing all kinds of science and STEM training for teachers, work with a bunch of students. Some of my colleagues are online as well, just to kind of monitor how things are going. So, but today we want to talk to you about a program that TI did a few years back in 2014, 2015, called STEM Behind Hollywood. And we're going to do one of the activities around that activity called, around that program rather, called Zombie Apocalypse. So, you know, there's a whole zombie genre has been going on for a long time. I mean, they really do not die. It's a fact. And so there's sort of this weird interest in you know, zombies and, you know, scary movies and that kind of thing. And so what TI did was we started working with a group by the name of the National Academy of Sciences. This is a big group and out of Washington, D.C. Basically, they inform government of new breakthroughs in science, medicine, and engineering. And they did a public outreach campaign about 10 years ago called the Science and Entertainment Exchange. Basically, what they do is they loan scientists to Hollywood producers and actors, actresses, in an attempt to try to bring some more credibility to some of the movies that make scientific feasibility. You know, making sure that the science is a little more real in the movies than movies have been in the past. So, for example, you may remember the Marvel movie Thor. Natalie Portman's character, she was an astrophysicist. Well, in the original script, she was actually a nurse that was going to take care of Thor, and they would fall in love and whatever. But the Science and Entertainment Exchange said, hey, look, we need to kind of try to bring some feasibility to the whole Rainbow Bridge thing. You know, basically how people from Thor's land zoom over to Earth. And so they used Natalie Portman as an astrophysicist to try to use wormholes as a mechanism for how, you know, the Rainbow Bridge works. So they do those kinds of things. They bring some really cool scientific expertise to the movies. Well, we worked with their scientists also. And believe it or not, they have a zombie expert. His name is Dr. Steven Schlossman. And Dr. Schlossman is a medical school professor at Harvard. So if you can imagine such a thing. So this is Dr. Schlossman right here. He's the guy in the white lab coat. He teaches psychiatry to medical students at Harvard. He also is a staff psychiatrist at Boston General Hospital in Boston, Massachusetts. So this guy knows his stuff. And the reason he got into zombies, there's a really interesting story there. It had to do with his wife recovering from cancer. There wasn't much he could do for her. It kept him up at night. He was watching a late night TV and he saw the very famous 1968 classic zombie movie called Night of the Living Dead. And it's black and white. It's the first big zombie movie ever. By the way, if you want to watch it, you know, make sure your parents are okay with it first. But it's available on YouTube. The producer of the movie failed to get any licensing protection, so now it's available for everybody to watch. And so you can check that out. It's a pretty cool movie. You know, it's old. Special effects aren't great, but if you can get past all of that, the storyline's very interesting. So Dr. Schlossman's watching this movie, and he's got a medical degree. He's an MD. And he's looking at these zombies and he's thinking, you know what, you know, instead of killing those zombies, maybe we should treat them as patients because they're sick. They've got something wrong with them. So he was looking at zombies from a medical perspective as opposed to, hey, these things are monsters. We need to take care of them, which was very interesting. Well, that stimulated him to write a book. And the book was called The Zombie Autopsies, Secret Notebooks of the Apocalypse. And you can Google that and get it on Amazon if you want to buy it. It's a fun little paperback book. It's pretty good. It's got a little medical terminology in it, but it's kind of a neat way to learn some of the science and math behind zombie apocalypse. So we worked with Dr. Schlossman. We read through his book, and he guided us on the creation of a couple of activities. One of those is Zombie Apocalypse Part 1. And you can use that on a TI graphing calculator or our software, and I'll show you a little bit about that later. And then also Zombie Apocalypse Part 2, The Humans Strike Back. So super cheesy, but a lot of fun. And we think hopefully you guys will enjoy it as well today as we walk through this activity. And we sort of reveal, all right, if we look at zombies as patients and not monsters, what can we learn, and how can we treat them? You know, what effect? Before you can treat a patient, you first have to diagnose what's wrong with them. You know, why are they sick? What's causing the illness? And in this time of COVID, this is sort of also a very timely activity. So I'm going to jump over to that. Hopefully you guys can see the title page here, Zombie Apocalypse, How Disease Spreads Through a Population. Edgar, let me know if you can't see that. I'm kind of assuming that everybody can see this.
We can see it.
Awesome, thank you. So again, this activity was written back in 2014. Obviously 2020 right now, everybody's hopefully recovering from COVID or avoiding COVID. But COVID in a lot of ways works just like any other contagion. So it goes through a population, it spreads from person to person. So this activity is sort of a way of understanding what's going on, okay, in general. Now, there's a lot, I want to make sure we separate fiction from fact. Zombies are not real. And in fact, Dr. Schlossman is required by Harvard at the beginning of every psychiatry medical school class. He has to publicly state in his classroom that zombies are not real. So I'm going to do the same here. Zombies are not real, but we're using them as kind of a fun, fictional way to talk about disease spread. All right. So here's the scenario. A new virus has been discovered that affects the brains of humans, basically turning them into zombies. So an epidemiologist is trying to figure out what to do to help stop the outbreak. Now, all of the STEM Behind Hollywood activities, and there's another series called STEM Behind Health, they are STEM because they focus in on STEM careers. So the whole point of this activity is, yes, to give you a little taste of the math and science behind these sort of fictional events. But another goal is to expose STEM careers to students. So middle school and high school students, most of the ones I know, and I've got a couple of high school kids, high school student age kids, they don't know what they want to be when they grow up. And so, adults are telling them, hey, you should do this, you should do that. And so these activities are meant to sort of put these careers in the context of what do they do? What does an epidemiologist even do? And if you can even pronounce epidemiology, you're doing pretty well. It's a big word. So an epidemiologist is sort of the main character of this activity, and they're trying to figure out, okay, there's a disease. We know it's turning humans into zombies. That's bad. What are we going to do to stop it? Well, what they know so far is they believe that it's a virus. They don't know for sure it's a virus, but they believe it's a virus. They know that it's airborne, and it's transported through saliva droplets of affected individuals. So this is the same basic mechanism that COVID uses to go from person to person, host to host. Okay, we refer to people that have been infected as hosts because they're a host for that virus or that pathogen to make more pathogens, basically to reproduce and make more. Okay, so zombies are attacking healthy humans as their primary food source. Also, they're creating new zombies from healthy humans. And so that's not good. See how the face and brain changes on page 1.6. So we'll get there in a second. It's a little creepy, but we'll get there. So in this fictional virus, we believe it affects the brain in 4 different areas. The one first is the cerebellum. And so the cerebellum is sort of on the back part of your brain, and it's in charge of your balance and coordination. So if your cerebellum's affected, it may have an effect on how you can walk, or if your hand-eye coordination is not very good. The other part is the hypothalamus. So the hypothalamus is sort of in the center part of your brain, and it's in charge of your appetite. The frontal lobe, the front part of your brain, is in charge of intelligence and problem solving. So it's kind of it's what makes you good at math and science and STEM. It's also responsible for being able to look at a situation or a problem and then come up with a solution to it. And finally, this weird word down here is amygdala. okay? Amygdala is how you pronounce it, and it's basically the emotion center of the brain. So our emotions are useful to us in a lot of ways. So if we're in trouble or if we have to fight back because we're being attacked, the amygdala is responsible for releasing a lot of the hormones that give you that sort of anger and rage that you might need to kind of fight back. Here's an image of all 4 areas of the brain. Obviously, your brain is not this color. This is all stylized. This is just to give you sort of a mapping between the area of the brain and then the actual how we colored these words. So these words have been colored according to the brain color that we're using. So here, so the frontal lobe is green, the cerebellum's blue, amygdala is red, and hypothalamus is orange. So when we flip back between these pages, you'll know what's what and where, you know, where it's supposed to be. All right, so when the cerebellum's affected, you know, the zombies clumsily shuffle forward. So you've seen some of these old movies where kind of the zombies are getting their arms out there, trying to kind of balance. Well, that's because their cerebellum's been affected. The hypothalamus means that they're very hungry. They're hungry all the time. They never become full, all right? And there's another whole host of reasons and points you can make about, well, yeah, but their stomach's basically disintegrating, and that's true. And we're not going to get too deep into this because it'll sort of unravel in a hurry. We're just going to focus in on the brain for now. The frontal lobe, poor problem solvers. How do you get away from a zombie? Well, you run to the nearest house, open the door, close the door. They can't get in because they can't figure out how to open the door. Amygdala, zombies aren't nice. They're full of rage and anger. They're not having a good day. And so they want to take it out on you. So here's that page 1.6. This gentleman, this is a real person. He actually works at TI. He's completely healthy, completely fine. He's not been infected with the zombie virus. We just used him as a way to, yeah, let's admit Harshal there. He's a person that just, he's our graphic designer, so he helped design some of the imagery here. Well, let's see what happens. Stage 1, healthy human, no infection, all is well. Brain's looking pretty good, other than being cut in half. You know, looking pretty good. Let's see what happens in stage 1. Okay, I'm going to pause it. Stage 1, he's looking a little gray. He's not looking so healthy. You can tell the brain's starting to shrink a little bit too. The frontal lobe, the cerebellum, that's not good. All right, stage 2, the frontal lobe and cerebellum are degrading. So notice that the frontal lobe is basically just kind of shrinking, and we refer to that as atrophy. So when body tissue has a sort of shrinking effect, it's not being used, it's not being, or it's infected, or it's you know, the tissue's degrading. We refer to that as it's in an atrophy, it's atrophying, it's shrinking, okay? And the same thing's happening on the cerebellum. Now the amygdala and the hypothalamus still look intact. They don't look like they're being affected right now. Let's get to stage 3. All right, this is not good. So Ryan's frontal lobe's pretty much gone. Cerebellum, that's ridiculous. And by the way, if this really happened, there's no way he'd be functional. Okay, this is losing this much brain tissue. It's unlikely that he'd be able to. I mean, he's pretty much dead at this point. But we're playing. You know, we're kind of riding the line between fiction and real. So you got to have to bear with me. So the real part of this is that, okay, if your frontal lobe is injured or something happens, it may affect your ability to reason and solve problems. If your cerebellum is damaged in some way, it may have an effect on your ability to balance. Your coordination, hand-eye coordination may be affected. Now notice the amygdala and the hypothalamus have been sort of color-coded a little bit to indicate that they're activated, okay? So they're working, they're still working. And in fact, they're not degrading whatsoever. Only the cerebellum and the cerebellum and the frontal lobe are being affected. Let's see what happens next. All right, we're full-blown zombie here. Poor Ryan. One, he's got these injuries that no Band-Aid will help. He just looks angry. I don't know what's going on with this eye thing over here. It looks pretty rough. And the brain's kind of just a big sort of head full of mush. There's nothing there. So I'm going to let this play a couple times so you guys can kind of watch through the stages. and see what's happening. And Edgar, I'd like to pause here to take any questions or comments that any of the students may have, or the teachers.
Yeah, are there any questions that I may be having right now? I actually read a couple questions if y'all don't have questions.
Yeah, do it.
I actually have why are we learning about zombies?
Yeah, it's a good question. One, they're fun. And two, we're using zombies as a way to sort of inform STEM careers. And so in this case, we're learning about an epidemiologist career. So what do epidemiologists have to do? Well, they have to work with medical professionals. You know, a lot of them work at the CDC, which you've probably heard a lot about in the news lately, which is the Centers for Disease Control. And so these are the folks these are the scientists who are responsible for trying to figure out strategies to keep a pandemic like we're in right now from happening. And if it does happen, what can they do to sort of mitigate it, to slow it down, to stop it? So you heard a lot of use of the term flattening the curve early on in the whole pandemic. And the whole goal of that was to socially distance, keep away from one another, so we didn't give the virus an opportunity to jump from one person to the next through saliva droplets, aerosol, just by talking or breathing. In some cases, depends on who you're listening to, but you know, trying to keep your hands sterilized from touching surfaces, because these things, the zombie stuff's completely fake, but it's sort of an engaging way to learn about careers like epidemiology. It's a good question. I think that's a reasonable question.
Yeah.
What else you have? Any other questions, or should I keep moving?
Yeah, we had a question. We had a comment actually from Vanessa. Zombies wouldn't last more than 2 days due to natural predators like maggots and heat.
Yeah. Well, that's a good point. And in this STEM Behind Hollywood program, we actually we do have an activity that gets into maggots. It's kind of, but it goes over some forensic science careers, and we work with a scientist by the name of Dr. Diane France. She's one of only 100 licensed forensic anthropologists in the world. It's a fascinating STEM career. She uses science and math all the time to try to figure out, you know, when they find remains of people from either a crime or just, you know, they fell off a cliff while they're hiking, which has happened. Dr. France is the one who shows up at the scene, looks at the bones. She'll evaluate those bones or tissue remains and try to figure out what's happening. A forensic entomologist is the person that looks at the maggots, the larvae, to try to figure out what species of blowfly is this, and what's their life cycle. So if I find a body with a bunch of maggots, and I know what the temperature and the humidity is, I can kind of figure out how long that body's been there. So in the case of zombies, I don't know if, you know, I've seen some movies where they have like the maggots in the flesh, which is kind of gross. Hope you guys aren't getting ready for one. So, you know, I think that's a good point. Like a zombie is basically a decaying, dying person. And so there should be maggots there that are doing what maggots do, which is basically, you know, consuming rotting flesh, bacteria that's forming, kind of cleaning things up. That's pretty gross. Sorry about that, everybody. I just, you know, it's science and STEM. This is how it works. Edgar,
One last question is Francisco P. Why did the back part of the brain change late?
Let's see. So the cerebellum here?
Yes. Or maybe the top part?
Okay, that frontal lobe. Oh, this part here.
Yes.
Okay, yeah. So, you know, the different parts of the brain, you've got the occipital lobe, which is back here. Yeah, the temporal lobe, which is on the sides, the frontal lobe. So that's a good question. So this is fiction, but if I had to guess, and this is just a hypothesis, I would say this part of the brain is probably suffering because it's not getting the blood and nutrients that it may need. You know, a lot of these systems are tied together, and so if the blood flow is not flowing to the brain, you're going to get this degradation regardless, because the brain has to have oxygen, and the blood's what delivers the oxygen. Good question. And I'm spitballing there, so you know, I'm just making stuff up. Any other questions? or should we keep moving?
I have a question.
Okay.
Do they get more hair on top of their head if they become a zombie? Like, does it grow faster?
It doesn't actually grow. What's happening? That's a great question, because I've heard this before, that when someone passes away, it looks like their hair grows. What's actually happening is, as the body loses moisture, as it sorts, right now when you have a drink of water, all your cells get water, and they're fully in size. But when a body passes away, a lot of times it becomes dehydrated, and dehydration will sort of retract the tissue, it pulls it back, and so it gives the appearance that the hair's growing. The hair is kind of growing in a way, but it's actually because of the retraction of the tissue of the person. It's a good question. By the way, since we're talking about hair, my coworker here, Ryan, he does have a mohawk, or at least he used to have a mohawk. But like a lot of us guys, as we get older, our hair starts to thin on top. So Ryan no longer has this mohawk. This was back in 2014. Ryan is completely bald now. Poor guy. So only hair anyway. All right, I'm going to keep moving on here. So Edgar, if you get any big questions or something, you can interrupt me, and I'll pause, and we can talk about what's next.
Sounds good.
All right, next page. So okay, we've got zombies. It's a problem. You saw Ryan turning into a zombie, very scary. Learn a little bit about the areas of the brain. So hopefully that's, if that's new information to you, that's kind of neat. But what we're going to do now is we're going to look at the actual epidemic or pandemic that's happening. So on this graph, I've got data points over a number of weeks, so up to 10 weeks, and I've got a number of zombies here on the y-axis. And so let's see, so the numbers are going up in kind of a non-linear way. So I'm not making really a straight line here. This is sort of accelerating quite a bit. Now I want you to pay attention to the y-axis. 60,000 is the number here. It actually goes up to about 65,000. If I hover over this point, looks like at week 10, I've got 59,292 zombies. Okay, so these are infected humans. These are humans that have the disease. And so I want you guys to look, see that weeks 1 through 7, everything doesn't look too bad, but then all of a sudden it just kind of explodes. What's going on there? Like, why does it look pretty good here, and then all of a sudden it just jumps up quite a bit, right? So keep that, keep thinking about that question. I'm going to jump over to page 1.9. I don't know. All right. I think it sounded like we had a zombie on the line there. Hopefully you're doing okay. Question 1, the greatest rate of infection occurred between week blank and week blank. And so if we go back to the graph, you guys can take a look and say, okay, we're looking at the rate. So the greatest rate is basically going to be the greatest change in the number of zombies over a 1 week period. So it looks like the greatest rate is going to be between weeks 9 and weeks 10. Okay. Question 2, what is the approximate infection rate between weeks 1 and week 6? So to figure that out, basically you would say, okay, I've got 732 zombies here. I've got 3 zombies there. So you just subtract the big number from the small number of zombies and then divide by the number of weeks, and you can get yourself an average number there. All right. I'm going to skip around a little bit. I want to jump over to page 12. And I want you to look at this graph for a second. Now it may look different than the graph we were on before, right? Like this one bumps up sooner, right? It bumps up at week 6. But what's different about this graph than the graph we saw before? Okay, well, we said the red dots look like they go up a little faster, a little sooner. What else is different though? Number of weeks is the same. But what about this y-axis over here, okay? This vertical axis. Well, if we compare it to this one, 60,000, 65,000. And then this one is about 1,000, okay? So would you believe me if I told you that this data is exactly the same data as this? Well, then why do they look so different? Okay, because this data is going up pretty quick versus this data. All right, this looks pretty flat. Well, the reason that's the case is because of this scale. All right, so the y-axis is scaled differently on this page than it is on this page. In this page, we only go up to 1,000. On the other page, we went up to 65,000, or 65,000. But let's take a look here. Let's look at week 6. At week 6, we had 732 zombies. At week 5, we had 244 zombies on this graph. And let's bump back up to this graph here. On this one at week 6, 732, 244. So why the difference in the way it looks? Well, I'm going to show you. And this is, the reason I'm emphasizing this is because when you look at data, when you look at a graph on the news, or a graph that your teacher gives you, or a graph that you make for a lab report, it's very important that you pay attention to scale. So what I'm doing now is I'm increasing the scale of the y-axis. Okay, and I'm going to pull it down here until we get to 60, about the same as what we were on the other graph. All right, let's see. So that's the same data, right? If you look at this graph, and then I jump back over to this one, they look pretty much identical. And so the scale is important. So even though this looks flat down here, it looks flat because the scale is so much larger. But if you actually go number to number, 3, 9, 27, 81, 244, 732, how fast are the zombies multiplying? If I go from 3 to 9 to 27 to 81, what's happening there? What's the rate of increase? And I'm not going to answer that question. I'm going to let you guys think about that. Think about those numbers again: 3, 9, 27, 81, and so on. What's going on there? All right. Edgar, if anybody wants to answer that in the chat, that's fine. Just let me know if you start seeing some answers flying in, and just interrupt me and we can talk a little bit about that. Otherwise, I'm going to keep going.
We see some. I see some answers. Valentin C, multiplying by 3. And if y'all want to take a stab at answering just put it in the chat, and then maybe we can do some. We can go through, see what you all put, your ideas. So I see Juan D. Ambris, the rate of increase is around 3.
Absolutely. Yeah, Juan's absolutely correct. Good job, Juan. So yeah, rate is, so basically what's happening is every week we're increasing by a multiple of 3. So we went from 3 zombies to 9 zombies, 9 zombies to 27 zombies. You know, you multiply 27 times 3, you're going to get 81, and so on and so forth. So it's sort of this this weird effect. And when that happens, when you're multiplying by a factor of 2 or 3 or 4 or whatever, something interesting happens. As you keep multiplying by a factor of 3 from the week prior, you get this neat looking graph. Okay, and you know, at first, if you were to guess, if I would have said to you, okay, draw me a graph of what you think the zombie population increase is going to look like. A lot of people may draw like a straight line like this, you know, it may kind of go like that. But that's not what happens. When you use a factor of 3, you get this kind of graph. If you use a factor of 2, you get a different kind of graph. Does anybody know what this kind of graph is called?
Anyone want to put it in the chat? Take a stab
Yeah, just
at
put
it?
that in the chat.
I know Sebastian put the graph would be exponential.
Yeah, that's exactly correct. Yeah, was the right answer. Because we're using an exponent, right, on a number to increase. So if you look at, like, if you guys have done exponents yet, some of you may not have, and that's fine. You know, but if I have, you know, 2 to the 3rd power, well, that means that I multiply 2 times 2, right? And so that number is going to get pretty big pretty fast. And so as you use exponents, you get this kind of graph. An exponential graph is not a linear graph, it's a nonlinear graph. And so some of you may have had algebra, you might have learned about exponents. Others haven't yet, but this is a little an introduction to it. This is real world math. So pandemics and epidemics and disease spread, we measure what's happening using graphs and data, and then we use the data, we look at the graphs and we say, okay, look, I know what this is doing. This is multiplying by a factor of 3, okay, by an exponent of 3. And so we use mathematics to try to diagnose what's happening, so then we can figure out what to do about it. And so that's why the math and the science and understanding that stuff is really important. All right, good. Yeah, good job. This class is engaged. You guys are doing great. I'm going to keep moving here. Let's see, we're going to get to right here. So eventually the rate of infection of any disease begins to decrease due to fewer and fewer people remaining to be infected with the disease. So again, when we talk about flattening the curve, this is what we are trying to get to. We are trying to get to the point where, you know, we level that graph out more quickly. So, you know, we're trying to avoid this. So if we can flatten this graph out down here, you know, it's a lot fewer people that are infected. And so all the measures that the CDC used and the World Health Organization that they were using and suggesting and trying to get people to adhere to was mainly to avoid people being in these kinds of numbers. Okay. Now worldwide, COVID's done some damage. A lot of people have lost their lives as a result of it. But proper hand washing, trying to use good practices when you're in public places, those kinds of things are important to try to avoid spreading, transmitting the disease from one person to the next. So that's what they mean by flatten the curve. We don't want curves like this. We want to avoid that. And so that's what we try to do. All right, let me jump over here, page 2.1. We're going to learn a new concept called virulence. So it's this word that's bold down here, virulence. You'll notice it looks like virus. It looks very similar. And basically, virulence is a measure of how effectively a pathogen, a disease-causing agent, can spread through a population. So basically, the more virulent a pathogen is, the faster it's going to spread through a population. I think they're still monitoring COVID, trying to figure out what's its virulence. There's a factor called it's R factor that you may have heard about in the news. It's similar, but not completely the same. But basically, COVID, people seem to get infected by COVID pretty easily, but depending on your underlying health conditions and your age, those kinds of things are risk factors for being infected or expressing symptoms as a result of being infected. Apparently, there's a bunch of people, younger people, 60 or below, that may have it, but they don't necessarily express symptoms. So it's been a very interesting disease in that regard. All right, I'm going to jump over to this page. We have another simulation. And by the way, a quick note on simulations. Simulations are tools. They're meant to help us understand what's happening in the real world, especially in a complex system. So we use simulations like for the weather all the time. I think there's a tropical storm that's down in the Gulf right now that's heading toward Louisiana. So they're taking proper, precautions to avoid, storm surge and that kind of thing. But we always use simulations to try to predict where a storm may hit. And we do the same thing with pandemics and epidemics. So with COVID early on, they were expecting a lot of, a high death rate. Luckily, the CDC just posted recently that I think they said that the mortality rates, instead of being 3.4%, it's more like 0.2%, 0.26%, I think, is the latest number. Hopefully that keeps coming down. We'll see. But what the simulation does is meant to kind of give you an idea of how the disease may spread through a population. So scientists use simulations all the time. It's just very, very important to realize that a simulation doesn't predict reality 100% of the time. It depends on who's making it, how much of the variables we understand, how much one variable may affect another variable. You just, you have to be careful with simulations with what you're told, because some of it may be worse or may be better. We don't know. The storm may end up over here, or it might end up over there. We just don't know. But it helps us kind of funnel down the probability of what may actually happen. So keep that in mind. Now we're going to start with a virulence of 1, and you can go all the way up to 10. And this is just a loose sort of factor that we came up with. But the white dots, the white little squares, are healthy humans. The orange squares are humans that have been infected but aren't yet expressing symptoms. And then the red squares are full out zombies. They have the disease. And what you're noticing is sort of how the disease is spreading through this population kind of slowly. The graph that's forming on the right side of the screen there, you can see that it's going up sort of exponentially, but then it doesn't stay exponential. It starts to level off up here. And so the question is why does it level off? Now, I mentioned this earlier, so if you're paying attention, you probably caught it. So why does the graph not stay exponential? How come it starts to do this? It starts to level off. And Edgar, just monitor the chat if you would. If anybody wants to take a stab at answering that, please do. I'm going to keep rolling. And Edgar, if you get some answers that you think you want to share, let me know. Just interrupt me and I'll stop talking.
Sounds good.
So look at this chart here. So we have all these red dots. These are all zombies. We also have some white dots. These are still healthy humans. I'd like you guys to provide some possible explanations as to why there are still healthy humans here when the vast majority of people have been turned into zombies. So there's 2 questions that are out there. One is, why does this graph flatten out up here? And the second question is, why are there still healthy humans in this simulation?
So I see 2 people have responded. Francisco P, less people are getting infected because there are barely any humans. And Ashley A, it levels off because there might not be any more to be infected, or because there have been some things set up to slow down the growth. Nice.
Yeah, I think those are both outstanding answers. Those are great answers. I love that. So, yeah, Francisco, I think is correct. If you look at this chart, there's only a few healthy humans left, little pockets of them. So naturally, the rate's going to go down because there just aren't as many people available to get the disease, right? There's a loose analogy here if you think about a predator-prey relationship. So a wolf and a rabbit, right? So the wolf eats the rabbits. And if there's 100 rabbits and there's, 1 wolf, or let's say 10 wolves, the 10 wolves will eat, the rabbits. If the rabbits don't reproduce fast enough to keep the rabbit supply up, what's going to happen? Well, the wolves run out of rabbits. So what's going to happen to the wolves? Well, they're going to start dying off and then that gives the rabbits a chance to build their population back up, and it's sort of the cycle. But this graph itself looks very similar to what you might expect. If the rabbits start running low, there's just not as many rabbits to eat. And so in this case of zombies, there aren't as many people to infect. So right on the money there. Now, what about some explanations as to why there's still white squares left? What's going on there? How come these people aren't infected? And while you guys are answering that question, I'm just going to kind of keep moving here. Edgar, let me know if you get an answer there.
Sounds good.
Bunch of different possibilities. So there's not just one right answer. All right, on this chart, what you see, when we ran the simulation, humans are these little blue squares, zombies are the red dots. And we get these really kind of neat looking curves. So the humans dropped off pretty quick, and then the rate at which humans were getting infected actually slowed down. So there's still a bunch of humans here, but the rate at which they were getting infected slowed down because they're not in the proximity of the zombies anymore, not as easily. There aren't as many healthy humans around any one zombie at that time as there were up here. Here, there's very few zombies, lots of humans, lots of people to infect. As that starts to change, that's why you see this sort of decay of this curve. The rate changes, it slows way down. And then the same thing, but inversely, the rate of zombies formation starts to slow down. So these are basically reflections of one another. And if you think about it, it makes total sense. So I have way fewer humans. I have way more zombies. The human rate of infection slowed way down. The zombie formation rate slowed way down because the zombies rely on the humans. All right, the humans are sort of the zombies are the dependent variable here. They depend on the humans. And basically, these are one and the same. Of course, it's the same individual. But from a graphical point of view, this is just a nice way to kind of visualize what's happening. Edgar, any takers on trying to explain what these white squares are?
Yeah, Ashley A brought up, could it be because they have stronger immune systems to kill off the infections?
I think that's a very possible reason. I think maybe they have some natural immunity already, and they have antibodies against the virus. I think that's a very good explanation. Any others?
No, that's it.
All right.
Far. If you do have any ideas, y'all please just share it in the chat, and then I'll bring it up to Eric.
Yeah, I'll let that go for a couple more minutes, and then I'll share with you some of the explanations I've heard in the past when we've done this activity. They're actually kind of cool. All right, so let's see. Question 5. In the graph, quote unquote, time is the independent variable, but there is no actual unit of time indicated. What do you think would be an appropriate unit of time for the spread of the zombie virus? So you see, this is what we're talking about. So we just said time here, but we didn't say days or weeks or months or anything like that. If you think about COVID, COVID, a lot of us have been on lockdown now since middle of March, I believe. And the numbers have still risen. But hopefully not at the rate that they could have risen if we hadn't been locked down. I think there's probably a debate there to have, but we'll assume that the numbers were flattened a little bit as a result of the lockdown. But so we've been in lockdown for a couple of months, but it seemed like we were getting kind of a daily update on the numbers of people that were infected. So I think this number, based on what's going on here and the sort of the rapid rate, you could probably make an argument based on this population that this is probably, this could be days or it could be weeks. Just depends on a couple of factors, and virulence is probably one of those factors. Now I want to do something real quick here. So we did a virulence of 1. You saw the graph kind of did this weird sort of thing here when it flattened out on top. Now, because I'm a guy who likes to go to the extremes just to see what happens. Let's go to virulence of 10. And so we crank that thing up. We're going to run the simulation. And let's see what happens. Okay. So our graph, when we did it at 1, was stretched out all the way across this screen. You guys remember? Now the graph, same amount of space, same number of weeks or days or whatever we wanted to define this as, but now it stops. It stops at 12. So let's say this is days, then at 12 days, it stops right there. So virulence of 10, obviously the infection happens much more quickly, spreads through the population much more quickly. That's not good. All right, so when you talk about flattening the curve and slowing things down a little bit, this is not that. This could have been maybe what would have happened had we not done some of the preventative measures that we did. So that's why we listen to the epidemiologists. Edgar, any other explanations on these white squares here, these healthy humans that didn't get infected?
Yeah, so we had Rodney H say maybe because the zombies have been eaten by the maggots.
I haven't heard. That's a new one. That's an interesting one. So, well, if the healthy humans were eaten by maggots, chances are they're not healthy humans anymore. But I like the explanation. I like the attempt. That was good.
Yeah, I did have one thing that I was gonna actually pose to the class is that I don't know if anyone else noticed in the simulation, the difference is where those white squares are located. There's a difference between that other one when you did that simulation and this one. Is there a reason for that?
Yeah, it's a good observation. And you know, the short answer is no. It's a randomly generated kind of thing that happens behind the scenes. But I appreciate the observation's good. I mean, you know, why did that happen? And would that happen in real life? Would you get like kind of this pocket of humans that just aren't, you know, they're just immune to the virus? I think the answer is possibly yes. I think genetics does play a factor. And so there's either a geographic reason, maybe these people are isolated, maybe they're behind locked doors. You know, they knew the zombies were coming after them, so they shut themselves away. It could be that the natural immunity thing, you know, because of genetics perhaps, or maybe they had some kind of infection prior that was close enough to the zombie virus that was asymptomatic. There's a bunch of different explanations, but the reason we have this in here is because this always happens. You always have this situation where, for whatever reason, some people get it and some people don't, or their bodies can deal with it more effectively. And it's just a very interesting kind of thing to talk about and explore. And epidemiologists, they ask these questions like, why is this, this group of people that are, genetically similar, they don't get the disease, but this other group of people, they're more susceptible to a disease. It's just interesting how genetics has a role in immunity. Very cool. Any other questions? I think we're running out of time here. Any other questions for me? All right. Well, let me wrap up with this. So just to kind of wet your whistle a little bit here. So the Zombie Virus Inoculation Task Force are frantically working to develop a vaccine that will combat the further spread of the virus. And historically, what other devastating diseases were brought under control through the development of a vaccine? Polio is a big one. I think back when I was a kid, the way we dealt with chickenpox is we just got chickenpox. We waited a few days and got over the itchiness and dealt with it. Nowadays, there's a vaccine for chickenpox so you get, kids today, they have it so easy. They don't have to have chickenpox. But that's the point is we try to, when these viruses pop up, we try to develop vaccines, inoculate people against the pathogen, and then we have a healthier population as a result. But think about these questions. Students, ask your family about, hey, when you were a kid, did you get chickenpox? These pathogens are all around us all the time. And most of the times our immune systems deal with them pretty well. But it's a fascinating career to get into, epidemiology. And so I encourage you to look into it, check it out. CDC has a lot of cool resources you can check on in terms of like careers at the CDC. And with that, I think I'm out of time. Cynthia or Edgar.
I was gonna ask one last thing, Eric.
Yeah.
I know some students may have questions that are relevant to your career. Can you answer a few of those?
Oh.
Possibly 3, 4?
Sure. Yeah, absolutely.
If y'all have any questions about the career, write them in the chat.
Yeah, and I can give you kind of a real quick kind of my background. I've been working in education technology for about 20 years. Before that, I was a high school biology and physics teacher. I have a master's degree in biotechnology and genetics that I got at the University of South Florida and the University of Texas at Dallas. So I've kind of taken some of my science background and my education background, and that's why I'm working at TI and the Education Technology Division. Is I help write some of these activities, do a lot of the training, work with students on these things, work with my colleagues in developing fun STEM activities using microcontrollers and robotic vehicles. We do a lot of really neat things at TI.
And then TI, just I mentioned it at the beginning, is Texas Instruments. And then Juan D. Ambris has a question about how long were you a teacher for in Florida?
Yeah, I taught for about 4 years in Fort Lauderdale. I taught for a year at in the west coast of Florida, just for my internships and things like that. To become a teacher, you have to do an internship, work with an experienced teacher to learn the sort of the ins and outs of being a teacher. It's not just knowing the content. You also have to know how to work with kids and how to get them to want to know more about a particular topic, try to engage them any way you possibly can. And so I learned a lot of that in my teacher training. And then my first year teaching, I had a mentor teacher that worked with me. She would come in every other day, observe me, give me advice. And then from there, taught a couple more years and then transitioned over to a scientific supply house where I wrote curriculum and helped build cool apparatus with electricity. So like things like the Van de Graaff generator where you put your hand on it and your hair stands up. So we designed some of those things and we designed a hovercraft with some plywood and some plastic and a leaf blower so you can kind of float around tile floor. We did those kinds of things. And then coming to TI, it was all about developing content that can be used on TI software and TI graphing calculators. And this activity, by the way, you can use on the TI 84 Plus CE. You can use it on the TI Inspire. You can use the software. If you go to our website at education.ti.com, you can even download the software, download the activity for free right now. We're doing a special promotion on the software. You just download it and use it.
And then I'll also be providing those links to the teachers and then they can share them with you all. One last question is, I know you hit on Richie's, like, how is it to work at Texas Instruments a little bit? Alejandra also had a question about how many years did you go to college?
More than I should have. So I was for my undergraduate degree, I've got a degree in biology and another one in secondary science education. So it took me 5 years to get both of those degrees. And then I did some research up at the University of Akron for graduate research, looking at, I was up there for a couple of years working in the lab. We were looking at different genes on with rats. And so we were using rat DNA. Actually, we're looking at RNA, and we're looking at the Y chromosome there's a gene on the Y chromosome that we think causes basically high blood pressure, essential hypertension. And so I did some research, worked in a lab for a couple of years doing that. Then I moved down to Texas, went to University of Texas at Dallas, and transferred what I could from Akron, finished up with a master's degree in biotechnology and genetics. So all in all, I was in my bachelor's degree was 5 years, and the master's degree took about 3. So about off and on about 8 years.
Gotcha. Okay. Thank you.
Most people can do that in 6, by the way. So don't use me as a model. You can do their bachelor's in 4, and then their master's in a year and a half to a couple of years. It just took me a little while longer.
Yeah. Thank you. Thank you for that. Thank you for sharing. There's no more questions. I do want to allow Cynthia, if there's anything that you need to say before we all log off. I do want to let all students know that when we do finish this meeting, please leave this meeting and then go back to your classrooms using the Zoom link that you're provided to log into that first day. So if